So today we study something called simple harmonic motion. How many of you have heard that term before? Simple harmonic motion. In other than physics. In other than physics. Sometimes you hear it in math. Sometimes you hear it in math. Basically, simple harmonic motion. Okay, get used to this. SHM. This is gonna be a very like FBD. This is gonna be a very famous or well-known acronym or abbreviation that gets used in first year math and physics as well. Okay, it's a periodic motion. What's the definition of periodic motion? Any periodic motion does what basically? One feature. What does it do? Yes. Repeats itself exactly. Repeats itself exactly. Okay. However, if you actually have what we call simple harmonic motion, it is a periodic motion, which means it's a behavior that repeats itself, but with one important condition. Everyone, one important condition that makes it simple, and that is it vibrates or cycles or repeats itself at what? At one single frequency. One single frequency. And the reason I'm asking why, if anyone had heard of simple harmonic motion before in math courses, is because any sine or cosine wave, pure sine or a pure cosine wave, represents what? Represents what? Simple harmonic motion. Any basic sine or cosine wave. Okay? So let me show you what I mean. So a periodic motion that does not have a single frequency, but rather is comprised or made up of multiple frequencies, is your heartbeat. Okay? How many people know just with your finger? How does your heartbeat look like? Actually, you do have it on the handout. How does it look like? It never looks like this. If your heartbeat ever looks like this, that means only one thing. Actually, if you're dead, you're flatline. Means one thing. You are a machine. You're a machine. Okay? Because basically, what the reason that a heartbeat EKG or ECG electro. Do you want to know what ECG stands for? When you go to hospital, when they actually suspect something in your heart, they always run an ECG. So you know what ECG means? Electro. Cardio. Cardio basically is the Latin name for heart. Okay, cardio is Latin for. So that's why they call it when you do cardio, you're basically what? You're basically playing with your heartbeat. Okay. So basically, does this look like a sine or a cosine wave? Absolutely not. But does it look like a wave? Of course it looks like a wave because it actually what? It is a what? It is a periodic motion. You can actually see that. Oh, I can see what we like to call in math a block that basically you can keep copy paste. That is a periodic motion. Okay. So is your heartbeat. Okay. Something like this. Cardiologists and biomedical engineers and pacemaker designers and so on all have to understand this ECG wave. Okay. Everything. It's kind of like think of it this way. This is to cardiologists. What seismic waves are to geophysicists and geologists. Every geophysicist needs to understand what secondary waves and primary waves when an earthquake happens. Well, a cardiologist needs to understand exactly what this is, and generally any doctor, but a cardiologist really should be an expert in wave analysis. And cardiologists always they look at what we call the intervals, the PR interval, the ST, the QT, and so on and so forth. And depending on the time it takes for an interval to happen, they can actually tell if you have a heart defect or not, based on just how long it takes the heart basically to go between these three points. Okay, just heads up for anyone in the future who might do some medical sciences or some what do you call it, cardiovascular research. Okay, all right. So let me actually show you everyone. Eyes on the screen. You don't have to copy this, and the next slide actually is kind of like jumbled with all the stuff on it. So let me show you what it says. So a very easy way to portray instead of a simple. What are we gonna create now? What's the opposite of simple? Complex. So just like simple trinomial, complex trinomial when you do factoring. Okay? So the easiest thing, all you have to do is what? Add two waves, but of what kind of frequencies? Same or different? Different. Because if you add two waves with the exact same frequency, you just make the same single wave, but with what? With a bigger, what do you call the size of the wave? Come on, from grade 11. Amplitude, exactly. So you sketch a sine wave of a certain frequency. This represents an SHM. Why? Because it's a single frequency. Let's say y equals what? Sine of 2x. How many of you have seen the graph of y equals sine of 2x before? I need to see almost every hand here. Okay? Because everyone here is either taking calculus or functions or at least grade 11 functions. And sine and cosine graphing is a very important technique of all of these three courses. Okay? They call them trig functions. Okay? Not trig identities or trig shapes, trigonometric functions. Okay? So here's the first one. Look. Yep. This is what? This is a sine 2x. Okay? Now let's sketch another one. Now I'm going to sketch what? Sine of what? What happened to the frequency? Did it go down, stay the same, or go up? Okay, does anyone know how a higher frequency wave would look like compared to that? By the way, we're going to study a lot when we do waves and light about this, but just as a little introduction, can anyone tell me how should this graph change to actually accommodate sine of 4x? Anyone? These are the kind of questions that Mr. Schubert is going to keep asking until the end of the term. What happens when you increase the frequency? What should happen to the graph? Okay, here's another hint. What should happen to the peaks of the graph? Ahmed. Say again? Ahmed went this way. Ahmed, you're telling me that the amplitude increases. Everyone, where is the amplitude in a sine or a cosine equation? Come on. Where is the amplitude? Is it inside of the bracket or outside of the function? Where is the amplitude? Come on. It's what? It's outside. The amplitude, everyone, is the number that precedes the what? That goes before the what? The sine or the cosine. What's the number technically here? What's the number here? So that means what? The amplitude of the wave is still what? Which makes sense because it goes up to 1 and sinks down to what? -1, because that's the range of a sine or a cosine wave. So it's not an issue of what? Of the vertical size. So what's going to happen to the horizontal size? Is it going to be more stretched or more compressed? How many people say compressed? Yes, when you increase the frequency, this has to what? This has to get more compressed, or the wavelength has to get what? Bigger or smaller? Smaller, because peak to peak distance is what we call wavelength. Okay, there we go. Hold on. Sine 4x should be. Did I change the scale? 2. Oh, I must actually what? This should have appeared before that. This should appear before that, because we know the more frequency you get, the more squeezed the function gets. Okay, what am I going to do with these two? What am I going to do? Add the two. Okay, by the way, when you add them, do they have the same frequency or different ones? No. By the way, do the peaks sometimes line up? Sometimes. Yes, sometimes, but not all the time. And because they don't line up all the time, you are going to generate this thing. Is this a simple or a complex harmonic motion? Does this look like a perfect sine or a cosine wave? No. Why? Because every block has technically how many peaks? 2. A sine wave per block has how many peaks only? 1 single peak. Imagine if you kept adding. By the way, what's the only thing that we changed between the two expressions? Only the what? Only the what? Only the frequency, or basically the compression of the what? Of the horizontal axis. Imagine if we changed so many other things. What else could we change? What Ahmed said, we could change the what? I could change the amplitude. Maybe there is more. Maybe there is more power, or maybe there's more weight or influence of this wave than this wave. So maybe I would make the amplitude here maybe 10, and this stays at 1. What else could I change? Come on. Come on, just think. What could you change? Remember, transformations. You did transformations in grade 10 and grade 11, at least in grade 11. How could you transform the expression of a function? Come on. A, K, C, D. So what could I do to this? I could shift. Yes. I could maybe shift this one plus or minus what? A certain amount. So that means it would shift, which would definitely change the what? The location or the actual behavior of all of these peaks. What else could I change? I could add a minus here, for example, which would make it what? Which would make it what? What we call a vertical flipping, right? Or a vertical reflection about the x-axis, like this. Okay? So you can change so much, and the more you change, the more you can model what? Yeah, the more you can model complex waves. Complex waves. Okay? One more thing about, yes. So there you go. Okay? Complex multi-frequency harmonic motion. We do not study these. Don't worry. Who are the best people to actually do wave analysis? Basically, electrical engineering, because they always deal with what? They always deal with what we call alternating current, not direct current. Direct current is what you get from a battery, like a 9-volt battery, or a 3-volt, or 1.5 volt, AAA, AA. This is called what? Alternating current. So they deal a lot with waves. Digital signal processing. Those people are the ones who actually take this wave and break it down to what? The original ones. Okay, there are so many techniques for this. You study them in engineering or physics or applied math, like I did. Or what? Astrophysics. Why do you think astrophysics deal a lot with waves? Astrophysics. What can you detect from stars and the sun? Well, the sun is a star. Yes, anyone? What do you detect from stars? Electromagnetic what? Waves. Boom. So they actually what? By breaking it down, they actually can know, oh, is this wave more infrared, more ultraviolet, and so on and so forth. Okay, yes.
I guess you could say like optics, we're going to study how it's coming from the millions of light years away.
Exactly, yes. But they actually do more with what? With analyzing, because you know that when a star gives a certain light that depicts it, what that actually tells you about its composition, right? Like is it more hydrogen, or is it more, for example, oxygen, and so what's burning in that star, and so on. Perfect. All right. So with that, okay, everyone. So the only kind of harmonic motion we will study is things that are related to what? By the way, what is the only thing that we study that has elastic energy in it? It's actually on the diagram. A spring, exactly, yes. So here, we are going to what? We are going to use only two things. We're going to use a spring, but attached to the spring all the time is a what? Is a small mass. Okay? But it has to be what to it? Has to be what? Has to be attached the whole time. Okay? So it's not like the question where the spring pushes and then suddenly what happens to the mass? It leaves it and it steals the energy from it and keeps going forever if there's no friction. Okay? So everyone, let's actually trace, this motion. Initially, what's happening to the system? Just look at that diagram. Is there any motion in the system? Is there any motion in the system in the first snapshot? No. But is there compression? Yes. By the way, what do you think this line represents? This dashed theoretical, hypothetical, imaginary line. What do you think it represents? Like, why do you think I added it to the diagram? To reflect what? Yes, Nora? Yes, the equilibrium position, or I like to call it the central position. Okay? So, question here. What is the only kind of energy in the first snapshot? So again, potential what? Remember, potential elastic energy. Which energy is zero? Okay. By the way, is this block changing its height at any moment? So the whole time, the EG could be set to be what? Zero. We could set the reference height to be the actual height of the system itself. Okay, everyone, look. So eyes on me. The first instant you're holding, then you let go. What's the spring gonna do? It's gonna what? Do this. So it's storing some energy. What's gonna happen now? It's gonna push in or out. You push this in, so that means it needs to what? To get back its natural height. Sorry, natural length. So it pushes out. Okay. As it's pushing, is there motion? So that means what? Is there EK now? Okay. What's happening to the EE though? Is it getting more compressed or less compressed as it moves out? Less compressed. So what's happening to the EE bar? Going down. Which means what's happening to the EK bar? It's going up because there's no friction and nothing is stealing energy from the system. Okay. Then it reaches right here. When it reaches here, the spring has gone back to its what? Original length, which means it is neither what nor what? It's neither compressed nor stretch. So that means the EE now is what? All the way down to? But the EK is the full. It's basically the maximum it could get. It shoots what? Over. What's the spring doing now? Is it pushing forward or starting to pull backward? But what's the spring going to do? Right here. After that, is it going to push forward or start to? It's still moving forward. But what's the spring starting to do? It's starting to what? To pull backward. So that means what? There is motion, but there is some stretching in it. Then it comes to a stop. What happens here now? Come on, wake up. Motion. No motion, and we're back to what? To full what? Full what energy? EK or EE? And we go back here. So you already have the entire description done. By the way, what do you call it when something goes back to the exact original point? We call that one what? Cycle. Yes, one vibration, one oscillation. Easiest word is one cycle. Yes, it cycles back. That's what they call cycle. So here, yep. Every other instant, it goes between what? Max and none for each. Max, none, none, max, max, none, none, max, max, none. In between, it has some of each. However, What's the most important principle? The whole time it's the what? It's the same what? It's the same total energy. Why? Because there's nothing lost out of the system and nothing gained into the system. All right. Okay, everyone, let's do an example now. So a 3.4 kilogram mass or block is attached to a spring with a stiffness. What does stiffness mean of a spring? What's another name for the, like what does it represent?
K.
K, yes. So the K of this spring is 164 newtons per meter, or what? It takes 164 newtons to stretch it by how many meters? 1, which you almost never do for a spring, but in case you are able to do 1 meter, you will need 164 newtons of force. Okay, so the first question is, the spring mass system is compressed by 12.3 centimeters and then released to exhibit or to reflect back and forth motion on a horizontal frictionless surface. Great. Question A. How fast in meters per second is the block moving as it passes the equilibrium central position? Okay. Initially, everyone, let's actually revisit this. Let's revisit this one. Right here. Initially, what was the only energy for the system before you released it? The total energy was made of what kind? Initially, before you released it. Exactly, elastic. So actually, let me go back here. Okay, so everyone, part A. They want you to relate how fast it's going as it passes the equilibrium. How fast it's passing the equilibrium. What kind of energy do you have at any equilibrium position? Like when it hits exactly the dash line. When it hits the dash line, what's the only energy that exists? Yes. Kinetic, because it's what it achieved maximum speed. So we can actually say it this way. Look. Okay, let's do it this way. I'm just gonna. Okay. All right. So for part A, how can we start this? Well, you can start describing. At first it had this. At the end it had this. Or you can always start with this. Look, everyone. ET equals. Okay, but we need to add some subscripts now. So what can we say? We can say ET initial equals ET what? We could say final, but could I also say ET equilibrium? Yeah, I can use any subscript I want as long as it's describing the instant I'm interested in. So I'm going to say that the ET initially is equal to the ET at the equilibrium. Okay, what are the only two energies in the system of interest to us? Only what and what? The system only has what kinds of energies? It technically has EG, but it's been zeroed out. Great. So everyone, we're going to go EK plus EE. Sorry, EKI. Remember, EKI, EEI must equal EK equilibrium plus E equilibrium. All right. Initially, which one of those is zero? Come on, let's cancel some stuff. Initially, which one? It had no motion. So everyone go ahead and just cross this one out. This one will be zero. As it passes through the equilibrium, what energy goes down to zero? Remember, they always switch. So now which energy is zero as it crosses the equilibrium?
Elastic.
The elastic, because it has no stretching, no compressing. Perfect. What's the equation for EE? All the time. Half. So half M, sorry, not M, my bad. Half K delta X squared, technically X initial, because it's I, equals, what's the equation for kinetic? Come on. Same structure. Half, yes, Amar? Half M V, I'm going to call it V equilibrium squared. Yep. What cancels out? Everyone, what's a common number in both sides? Half. Go ahead, cancel it out. Or that's basically what? Same thing as multiplying both equations. Sorry, not both equations. Both sides by 2. So either way, I don't really care. I'm going to cancel. Although math teachers wouldn't like that. Okay. Which one of those four things is the question asking me to find? Mass, K, displacement, or speed? Speed. So that means you need to arrange this one to calculate for this guy. Anyone can tell me the arranged expression? You can work it out in steps, but who can just see what it is? Raise your hand if you'd like to say it.
What is it?
Asking how would you, like what would be the expression just to solve for this guy? Farah? V eq. Yep, equals
Square root.
square root. K delta x squared over what? Done. All right, let's plug in some numbers. And remember, your numbers have to be standard in units. K is 160 what? 164. Okay. What's the compression that you're given? 12.3 what? Centimeters. Has to be converted to meters. So you divide by 100 or you get 0.123. All dividing what? What's the mass? 3.4 in kilos. Great. Everything, please make sure, is under the square root. Done. That's it. Let's do the calculation. Okay, I'll do the square first. 0.23 squared times 164 divided by 3.4, and you square root this guy. Done. What's the situation of all these numbers? 164 is how many? 3. 0.123. 3. Is it 3.4 or 3.40?
0.
Great. So all of them are what?
3.
3. What would this one be to 3 sig figs? 3 sig figs. 0.854. But in what unit? By the way, this is speed, and it's standard. It has to be meters per second. So equals 0.854 meters per second. Or how much in centimeters per second?
85.
Exactly. You multiply it by 100. So that basically is 85.4. Your block will never move faster than this speed anytime it's going back and forth. It will never be faster than this. Why? Because that's the maximum amount of speed it has, because that reflects the maximum amount of kinetic energy it could ever pass. Noura, what's part B? So how stretched in centimeters is the spring at the moment when the block is moving at 65 centimeters per second? Okay. What information do I know about the system right now? Displacement or speed? So what energy could I calculate right now? Kinetic. Which means I need the total energy of the system. Can you tell me from which instant can we calculate the total energy of the system? Usually, from which instant can you always know the total energy of the system, or can you calculate it? You never know it, but you can always calculate it. Which instance in the system usually allows you to calculate the total energy? From all of them, but which one usually is the easiest? Initial. Because initially, do we know everything about the system? Yes, we know. We had speed 0, and it had maximum what? Maximum compression. So, everyone, we're gonna say this here. So, for part B, everyone, for part B, we're gonna say that ET all the time. No, what can we say? I don't want to say all the time. ET always equals EK plus what? Plus EE at any moment. At any moment. Okay. ET always can be calculated from what? ET initial. All right. What do we know about the initial step? Come on. We know that EK is 0, but EE. So we can just say half K delta X squared. Initial must equal half M V squared at any moment plus half k delta x at any moment. That's it. We just need to solve this now. What can I cancel from all three? Half. Go ahead. Oops, sorry. Half, half, half. All right. Let's plug in numbers. K is, I'll do it in green, 164.123 squared equals 3.4. Do I know the speed at the part B? Am I given the speed in part B? No, in part B. Part B. Yes, in part B, they're telling me how fast the system is going. So I can use it, but they're giving to me in centimeters. I need to do it in what? Meters. So what would that decimal be? 0.65 squared. Plus 164 times what? Times delta x squared. We need to solve for the delta x squared. All right. How can I solve this? I just need to clean up. So now we're going to get the left side done first. So let's do this. What is it? 0.123 squared. 0.123 squared times 164. That's how much energy the system had all the time. Sorry, how much total energy the system will have all the time. Let's go with 2.481. 2.481 equals. Okay, how much kinetic energy does it have? Here, 0.65 squared times 3.4. 1.437. Yeah, 1.437. Plus. Okay, how would I solve this? Easy. We'll move this one here, subtract, divide by this guy, and then square root. So let's just do that on the calculator without writing much. Okay. All right. Oops, my bad. That implies delta x will be, okay, 2.481 subtract 1.437 divided by 164 and square root this guy. 0.0, okay, again 3 sig figs. How much would this number be in 3 sig figs?
0.
So basically you have to cut it here. 0.0798. 3 sig figs means the first zeros don't count, because you can always play with scientific notation and hop through it. 797, but the 8 will bump the last 7 to an 8. So 0.0798. In what unit though?
Meters.
But we want it in officially, that's what the question wanted, which would be what? Just hop the decimal point twice. You'll get what? 7.98 centimeters. What's the only logical check that this answer makes sense? Think, how much did you compress the system the first time? Like what was the maximum deviation from the equilibrium position you allow it to have? 12.3, which means what? By the way, could it ever bounce back to further than 12.3? No, because that means the what? That means there's more energy in the spring now to stretch, more than you gave it, which makes absolutely no sense. 12.3 this way, 12.3 this way, which means what? 7.98 is what? Is within the 0 to 12.3. Perfect. Ammar, what's part C? How similar is this question to the part B? Is it almost the same idea?
Well, it's sort of the opposite.
Thank you. Perfect. It's the first one. Oh, sorry. The part B. You were given the what?
Stretch.
No. This. The speed, and I asked you at that speed, how far is it from the what? From the equilibrium position. What do you have in part C?
We have
What?
the distance.
Exactly. I'm telling you now how far it is from the equilibrium position. You tell me how fast it's moving at that point. It's exactly the same amount of work. So everyone, are we still gonna start saying this? Yes. Are we gonna say this as well? Yes. Are we gonna say this as well? Yes. The only thing that's gonna change now is that instead of knowing this, I know this guy. So it's the same amount of work. Okay? So I'm just gonna leave it to you as well. By the way, what was your maximum speed anyway? Which was the maximum speed found in part A. What's the maximum speed this system could move at, Amar? 85.4 seconds. Could it ever move anywhere at faster than that speed? Which means your answer for part C has got to be slower than 85, once you convert to centimeters per second, has got to be slower than 85.4. It has to be, because some energy is still contained in the spring stretching. Perfect. That's all.